Welcome to your AP Statistics lesson on using the standard deviation as a ruler in the normal model, part 2. So the empirical rule is great at giving us an estimate of how likely observations are if the data values fall exactly 1, 2, or 3 standard deviations away from the mean. If we don't have that, we can use a table of normal percentiles. You'll hear them called the standard normal table. Or we can use normal CDF, the normal cumulative distribution function. And that is going to be our preferred method. It's much quicker and easier to remember how to do and use in the long run. But let's look at how table Z, the standard normal table, would be used. First, you would need to convert any observations to a Z-score. So let's say you did, and you need the area to the left of a Z-score of 1.8, or you need to know the percent of observations that are less than 1.8 standard deviations above the mean. On the Z table, you will see that there are, down the first column, and it should be marked Z, there are ones digits and tenths digits, excuse me. And so first thing you want to do is find that. In that first column, you want to find the row you are interested in. And then you'll notice at the very top, after it says Z, there is a row with markings of 0.00, 0.01, 0.02, up to 0.09. You just look at the hundredths digit for that because you already know your units digit and your tenths digit, so you just need the hundredths digit. And so you get 0.9641. That tells us 96.41% of observations fall below 1.80. Many calculators and statistics programs have these things programmed for us. It uses calculus to define these areas. We will not be using calculus to find these areas since this is a non-calculus based course. We will use our CAS, and we will learn how to do that later in the presentation. Sometimes we start with areas and need to find the corresponding Z-score or even the original data value. What Z-score represents the first quartile in a normal model. So the first quartile is the lowest 25% of observations. So the area to the left of that value for our Z-score would be 0.25. So now we're going to use the table in a different direction. What you do is you look for the area that is closest to 0.25, and let's go ahead and put 00 since there's four decimal places in our table entries. So 0.2514 is pretty close, and so the figure associated with that is negative 0.67. So we can use that. The first quartile is going to be 0.67 standard deviations below the mean. When you actually have your own data, you must check to see whether a normal model is reasonable. Looking at a histogram or a dot plot or stem and leaf diagram of the data is a good way to check that the underlying distribution is roughly unimodal and symmetric. And we can also use that normal probability plot that I had told you about in the last video. We'll actually look at that in this one. It is the more specialized graph that we introduced right here. A roughly normal distribution will be linearized to look like an approximately straight diagonal line. Deviations from a straight line indicate the distribution is not normal, and this is one of your options on the CAS. So here, let's compare. Here's the same data. Here's a histogram of the data. You can see, yeah, it's roughly symmetric. A couple of gaps here that could be concerning, but, pretty, no big departure from normality there. Single peak, symmetric, okay. It's plausible that this sample comes from a normal population. All right, we want to look for a straight line, and boom, these values cluster around a straight line. Now, it's not going to be perfectly straight, but this works pretty well. Now, again, notice this is kind of cool. these observations here that kind of made us go, huh, kind of make us go, huh, over here also. So here's a clearly skewed observation, skewed to the right. And if you look right here, there's a big old bend in the normal probability plot. Okay, if the distribution were normal, we'd expect it to be much more linear. So this indicates that a normal model is not appropriate. So let's look at some examples. What percent of a normal model is found in each region? We're going to draw a picture just because I want you to get the concept of what it is we're finding. All right, z greater than negative 2.05. Okay, just a quick sketch here. So that means negative 2.05 here. And then we want the area to the right. So what you'll do in your calculator is you'll do normal CDF. Okay, you need to go, you can be in the scratch pad. You're going to go to Menu, Statistics, Distributions, and scroll until you find normal CDF. When you click on that, you're going to be prompted for a lower bound. So you're going to do negative 2.05. And then an upper bound, you're going to put in infinity. There is a special symbols key down along the left-hand side of your calculator. You can get things like pi and that sort of thing. If you'll click on that, you can do infinity. If for some reason you're stuck on that, just put in like a really large number, like 999,999. That will approximate infinity well enough for our purposes. Okay, we don't need to change the mean or the standard deviation, so we're going to leave them as 0 and 1 because we are working with a standardized score. The calculator gives you 0.97981, blah, blah, blah. Typically, we round to 4 decimal places written as a proportion, since that will give us to the hundredths place when we write it as a percent. So 97.98%. What percent of a standard normal model is found where z is less than negative 0.33? So here, we want the area to the left of negative 0.33. So again, you're going to go to normal CDF. You're going to have negative infinity or negative 999,999 for your lower bound. Your upper bound is negative 0.33, and the calculator gives you the area of 0.3707, so 37.07%. Again, we left the mean and standard deviation as 0 and 1 because we are working with standardized scores. We can find the area between two endpoints, so 1.28 and 1.8. Again, we draw our little picture. Okay, both of these z-scores are to the right of our mean of 0, so it's going to be a small, interesting shape piece to know what percent of the observations lie there. All right, so again, you're going to do normal CDF. This time our lower bound will be 1.2, upper bound 1.8, and so that's going to give you what turns out to be 7.91%. All right, so let's look at a contextualized problem. Based on the normal model in 116 describing IQ scores, what percent of people's IQs would you expect to be over 80? Okay, for today, I want you to practice finding the z-scores. I'm also going to tell you what you can do if you're in a hurry, like on the AP exam, and they don't ask you for it specifically, how you can go ahead and get to the percentage. Okay? All right. But for today, you need to do this. So the z-score is observation minus mean over standard deviation. So 80 minus 100 over 16, which turns out to be negative 1.25. So negative 1.25 would be, to the left of 0, and we want the area to the right because we want over 80. So normal CDF, lower bound negative 1.25, upper bound of infinity, or 999,999, and so we get 89.44%. Okay. If you were actually doing this on the AP exam, you would need to show some work. You would need to explain what you're doing. One thing that we can do is write all the arguments that go into normal CDF, but you have to label them. So you'd either want to label it like we have here, or if you write them parenthetically underneath negative 1.25, you'd want to put LB for lower bound, UB for upper bound. The 0 is mu, and the standard deviation is 1. So mu underneath under 0, and sigma, baby sigma, under 1. Now, you've noticed that we haven't changed the mean and standard deviation on any of our problems because we've always worked from z-scores. And for today, I want you to do that. But moving forward, unless you're asked for that, you can simply put in the 80 and still go to infinity, and then change the mean to 100 and the standard deviation to 16, and it's going to give you the same probability. That's why standardizing works, is because it does give you the same probability that we would get if we did not standardize our scores. Okay, so under 90, again, today we're doing finding z-scores. So 90 minus 100 over 16 is negative 0.625. So again, here's a picture. Normal CDF, lower bound is negative infinity. Upper bound is negative 0.625. Again, we found the z-score, so we leave the mean 0, we leave the standard deviation 1, and we get 26.6%. So between 112 and 132. All right, these where there's 2 endpoints are really going to make you appreciate the fact that moving forward, you can use the calculator and just change the two, the mean and the standard deviation. We have to find the z-score for both endpoints. So it's a little bit of extra work. So for the lower one, we get 0.75. For the upper one, we get 2. So here we are, 0.75 to 2. We do our normal CDF, lower bound 0.75 to 2, leave the mean 0, leave the standard deviation 1, and you get 20.39%. All right. We want to work backwards. When you are working backwards, many times it is going to be extremely helpful for you to draw a picture first. It's harder to kind of just read what they're asking for and interpret it correctly. All right, in a standard normal model, what value or values of z cut off the region described? Remember to draw a picture first. So we want the lowest 12%. So the lowest 12% is over here. The area is 0.12. The cool thing in your calculator, still under menu statistics distributions, one of the distributions you can choose is inverse normal. Inverse normal only understands areas to the left. That's what we're finding here, is the area to the left of 0.12. And so you do inverse normal 0.12, and it gives you a z-score of negative 1.17. So there's where that would lie. The highest 30% means that we want an area over here to the right to be 0.3. Our calculator only understands areas to the left, so we do 1 minus 0.3 to get 0.7. And we do inverse normal of 0.7, and so we get a z-score of 0.52. So 0.52 is the cutoff point for the lowest 70% and the upper 30%. Highest 7%, same idea, okay, just to really drive this home. That's going to be the 0.07 is the area to the right, so 0.93 is the area to the left, and we get a z-score of 1.48. Okay, anytime this area to the left of your observation is less than 0.5, we expect a negative z-score. When the area to the left, like in this case, the area to the left is 0.93, we expect a positive z-score. If the area is exactly 0.5, you should get a z-score of 0. So middle 50% means we're going to go to the bottom. We want 25% to be lower and 25% to be higher because we're taking 50% out of the middle. This is where drawing a picture can be really, really helpful. Okay, so we've got 50% out of the middle. 100 minus 50% is 50%, divided equally into 2 tails, so 0.25. And so we're going to do inverse normal of 0.25 and then inverse normal of 0.5 plus 0.25, so 0.75. And we get negative 0.67 and positive 0.67. What would these be right here? Right. That is the first quartile and the third quartile of the standard normal distribution. All right, so let's put it in context. In the normal model, in 116, what cutoff bounds the highest 5% of all IQs? All right, so we want the highest 5%, and so we're going to subtract that from 1 to get 0.95, and we do inverse normal of 0.95, and that gives us 1.64. Okay, so now we know the z-score, we know the mean and standard deviation, we can figure out the observation. So you can call the observations X values or Y values, whichever way you want to call it. Your book uses Y values. I thought I had changed everything in here to X. It doesn't matter. It stands for observation minus mean over standard deviation, and that's going to equal 1.64. So you do your algebra, you multiply the 16 times 1.64, you add the 100, and you get Y or X, whatever symbol you're using for the observation, equals 126.24. The lowest 30% of all IQs, we're going to draw a picture first. We're going to do inverse normal since this one is giving us the area to the left, and so we get negative 0.52. We're going to go through that same process to convert it to X or Y, whatever you're calling your observation. So observation minus mean over standard deviation. We've got negative 0.52 equals Y minus 100 over 16. Multiply both sides by 16 and then add 100, and you get that your observation is 91.68. Middle 80%, we want a picture. So if we have 80% out of the middle, that means that there's 20% to divide evenly among the two tails. So 10% is, or 0.10 is to the left of the lower z-score, and 0.9 is to the left of the upper z-score, and you get negative 1.28 and positive 1.28, and then you convert both of those. So negative 1.28 gives us an observation of 79.52. Positive 1.28 gives us an observed IQ of 120.48. Okay, guys, try the problems to try on your own. Again, we will go over the problems to try on your own in class. Please, please, please make sure that your calculator is charged and ready to go and in your backpack and ready to be used during class. If you have any urgent questions, please send me an email or come by. I will see you in class, and I hope you have a great day.